Welcome to Wi-Fi Knowledge Summit. So we have a packed day, and as you know, many of you have been here earlier. We don't do any introductions. We don't have any gifts or bouquets for the speakers at the end, but the speakers we're really grateful for them to share their time and expertise. As a token of our appreciation, there will be a tree planted at 14 trees in the name. So we'll try and get Praveen sometime when we have some space to kind of share the 14 trees vision and maybe give you more idea. So without much ado, is there anything else? So a couple of notes, just there is a quiz. So keep watching, don't doze off. There will be a quiz whose results will be announced towards the end, so you'll have to stay till the end to get the prizes. That's one. There are mini quizzes where I hope we have got some chocolates, or we'll get some chocolates just to entice you back into the room after the breaks. You have to be again here. So any other notes, Nadeem, before we get started? Actually, I should acknowledge. So thanks to all our sponsors. So let me pull up one more here. Yes, I think this will cover all the partners. So I represent Nanocell. Of course, we have our Wi-Fi case organizing team who are running around. So maybe towards the end, we'll get everybody up to get an acknowledgement. 14 trees. Praveen Bhagwat was instrumental in actually getting this event started as such. So 14 trees is an initiative which he now spearheads. They are the sustainability partner. Of course, IEEE ComSoc has always been very helpful in getting the word out. But most importantly for us, we have sponsors of two categories, and all of them, Arista, HFCL, EmbedUR, Alithia, Netgear, Zylogic, Spirent, Keysight, all of them help us keep the costs down for the participants. Otherwise, we can't afford to run this at this venue, etc. So we thank them, and please visit their booths on the other side. The tea breaks and the lunch sessions will be there. We'll try and give you a little bit more time so that you can also spend time at the respective booths. Sponsors will also have some, at least the summit partners will have some videos shown during some of the slots, okay? So if there is no other announcement, I think I'll get started since we have a tight agenda and I have to hand over to the next speaker. So just give me a minute. So mine is going to be a very short presentation. Hopefully I'll be within time. So my name is Srikanth, and I just wanted to maybe do a short presentation on where we are going with respect to 802.11 and Wi-Fi, okay? So just to quickly look at the evolution, we are today in the Wi-Fi 7 era. It's the hot topic in everybody's mind. Of course, for those geos where 6 gigahertz is available, 6 gigahertz becomes very important. Of course, somebody was asking us yesterday during the pre-summit training, isn't it saturated? But I was telling that Wi-Fi 8 is already in the works. So we are hopefully getting there soon. And I had this last year as well. 60 gigahertz is getting more attention than before. Only thing is whether it will be translated into something meaningful in the near term, we'll see as we go along. The other intention of my short presentation is also to tie together some of the talks so that you can see a narrative for our whole day. So if we look at other important things other than the radio, because sometimes the radios get undue attention. Everybody talks about OFDMA and MU-MIMO as the only thing that we have done in Wi-Fi. That's not the case. In fact, I would argue that more importantly, things like security evolution, where we are in the era of WPA3, touching on 256-bit key encryption now, and lots of coexistence issues, because as you know in Wi-Fi we have to live with the past, and that is something that we have to learn to kind of do in a much more smoother way than what we've been doing. And apart from data transfer, we also have all these new age applications, sensing, location, ranging, awareness, etc. Luckily, we, at least in the location ranging, we have two presentations. One directly on Wi-Fi location, one UWB based from NXP and Arista. So I'm hoping that that will give us some idea of what might be the scope of things. Some of these have really not taken off to the extent maybe that has been envisaged. So I think there is some potential there. Of course, we will hear about multi-link in a couple of presentations, or one panel and another presentation where we'll see some simulation results telling us where this is going. In fact, now that you tell me, I just have to unmute for my online guys as well, whom I forgot. Just if you don't mind, just give me a minute. So since we were dabbling with our presentation, I forgot them. Sorry, Sumit and Hoin. So there they are. Yeah. So just hold on, Sumit. I'm still in my presentation. So let me finish mine and then hand over. Let me share my screen right now so that you can see what's going on. And then, okay. So that will also keep them in touch of what's going on. So multi-link, of course, we'll hear performance aspects in the panel discussion. We'll have some idea of some of the home happenings. I think Sai might share something from what's happening on the home side. We have open roaming, hopefully introduced to us again with HFCL. We might also have some more information from WBA in future events of Wi-Fi KS. So these are some of the topics where we are also delving on the other important things than just the radio-related enhancements. Okay. And as I said, one of the things is the big question in 6 gigahertz is, will India make a move? Maybe we'll get some points from some people who might know more. For those of you who might be following WRC, conveniently has left it to individual countries to pick whether go cellular or go Wi-Fi. The other thing that is new in 6 gigahertz, if your company is involved in outdoor or what we call standard power Wi-Fi, is this AFC-based usage has happened, started in the US. So this is, I think, very interesting because that probably has some lessons for us going ahead in terms of whether we can use unlicensed band with this kind of approach. And I overall think that 6 gigahertz might be one of the best news because getting spectrum has always been a challenge, and 6 gigahertz in fact has become contentious as well. And I'm hoping that with all the things that we have put in, we'll get better usage of that spectrum because 2G, 5G spectrum, as you know, more than data, we waste it with a lot of other things as well. Okay. So this is primarily to provoke some discussion, whether anything after Wi-Fi 4 or 5 has been useful, right? Because MU MIMO and OFDMA, I think Sumit also might have some points just after me, have really not shown to be that useful in practice. And scheduled uplink in Wi-Fi, in my opinion, Sumit, I'm just generally being a little provocative so that maybe somebody will have something else to say. And continuing on this thread, all this hype on MLO, I hope that that will not turn out to be something like what we have seen, and similarly preamble puncturing, etc. Okay, of course, you know the story that spatial reuse and TWT again have not really gone as far as we hoped. Okay, so and here is the other statement is that after 4 and 5, I'm making a statement that nothing has really happened usefully. And whatever I see for Wi-Fi 8 also is, I'm not very hopeful. But again, I will happy to be corrected or debated upon during the course of today, okay? So I would like to maybe points to keep in mind as to what we could maybe think about when people who are involved in standards and other things is, of course, Wi-Fi is predominantly an indoor dominated sort of environment technology. People might not know that it's a chipset-based ecosystem on both sides. So it's basically very cost-sensitive. Often I find people saying, oh, we are not even able to get an extra cent for embedding Wi-Fi in the laptop or whatever that is. For example, many people think that we have all these fancy MIMO, but we don't have a client which is anywhere close to this. Even though it's years, 11N, that's why I said after Wi-Fi 4, all those additions to MIMO has not really come to the mainstream, right? And I also think that, we also get sucked into comparisons with 5G, 6G, etc. URLLC, for those of you who know 5G, drones, satellites, and so many other things. Well, this is a tricky question. I'm not saying you should not use it. And there are people, I think, in this room who are using it. Even yesterday, somebody in class said, why don't we use the mid-amble? because we are using, I said, if one wants to use it, they can use it in some context, special case. I think we can leave that to implementation, and you will be surprised how people take Wi-Fi silicon and do lots of interesting things. But to make that as a mainstream case and pressurize the whole industry, I think is a tricky point, okay? And I think this will lead us directly to the next talk, because I think Wi-Fi does not do a very rigorous evaluation, because legacy is 90%, 95% when we introduce new. All our evaluation is as if we are all in Wi-Fi 7 world, except for some token backward compatibility feature. So I think rigorous evaluations of features in the presence of legacy with tools like NS3, about which we are going to hear next, I think might be very useful. So this is something that I'm hoping that we will do more before we pronounce success for any new feature, because this is something which will be important as we go along. And my final slide before I hand over, this I've said in another forum, in cellular forum also, somehow the 3GPP crowd hijacks 6G. I don't know why Wi-Fi people stand down and leave it, them trampled. It's almost like 3GPP is the owner of the Gs. But that's not the case. Most of our data, in fact, yesterday I read the statement that it's almost 90% now the data flows through Wi-Fi. So it's really that we should not let Wi-Fi, or in a certain extent, there are other technologies also which we use, right? And I would say, appeal to the cellular crowd in India, the news I get from all the people outside is the news which said, your operators want no blocking of 6 gigahertz equipment sale. That's the only news I get from people outside. So I think we should leave 6 gigahertz to unlicensed, right? Look at Wi-Fi as the technology to serve indoors or similar location, whether inside planes, trains, yards, etc., right? And including doing for IoT, sensing. In fact, for IoT, we'll have a talk on Matter today, which will see how Matter gets integrated as an application layer, pulling in Wi-Fi and other technology strength. Sensing is becoming 6G is one of important things. All these things, indoors and similar environments, why don't we use Wi-Fi as the starting point instead of trying a 6G solution for these things, okay? And remember, with energy usage, I think Wi-Fi has a sweet spot. When you are within an indoor or a similar space, Wi-Fi probably gets the bits to you with probably the least energy. So given that we are in the sustainability and all that things added on to the goals of next generation, I think Wi-Fi fits the bill in many such cases, okay? So I'll not take any questions, but I'll be coming again, so maybe some of this we can debate. So now I'll hand over to my next speaker. Sumit, are you ready? So you can share now, Sumit and How.
Is the audio check? Is the audio good?
Yeah, audio and screen are fine. You will have to bring your presentation. Can you share your presentation, please?
Sure. Yeah, start sharing.
Yeah, I think looks fine. Just make it full screen from your end, please. And I'll make full screen from my end. I think we are good to go. I'll stay muted and maybe give you a heads up just close to the ending time, okay? Over to you, Sumit. Yeah.
Your word. Okay, so How, next slide. So we've divided this into two sections. I'll just basically spend 10 minutes on section 1 and then leave How for the majority of the time to do the meat, which is, they describe the use of NS3 for network performance evaluation for various use cases and scenarios. Next slide. And Sri essentially set up, I think, our talk very nicely. So I will, in the next 10 slides, what I will try to do is sort of amplify what he said and kind of connect the technology dots. So from a Wi-Fi researcher, and by the way, besides being an academic professor, I've also worked in industry. As a matter of fact, I was a blue badge in Intel for about 3 years doing pre-Wi-Fi, pre-11 and Wi-Fi circa 2002 and 3. And have been a standards delegate. So I kind of know, sort of both sides, both in terms of the R&D as well as in terms of how it transitions to actual technology. So since Wi-Fi 5 AC, okay, the transition to 6 and 7 and now 8 has been really significant in the following sense. So, till Wi-Fi 5, we've already had this all-you-can-eat, peak capacity, peak throughput per user for a single link as sort of the major KPI. That's what gets advertised and written on the box. Since Wi-Fi 6 and thereafter, ever since the titular working group names changed to high efficiency or extremely high throughput, okay, etc., you know that the game has significantly changed because one, instead of a emphasis on a single link capacity, it's the focus. The KPIs have moved to aggregate network performance, right? And again, aggregate network throughput. And to support those goals, right, as you can see the list of new features, right, which has come out of the box, come out of the woodwork. And I'll just say this, I'll sort of club this into three big themes, all of which Srikanth mentioned. One was spatial reuse, right? The fact that increasingly Wi-Fi, moving from sort of single homes in a Western context, moving it into both the enterprise and in dense clustered apartment like scenarios, that use case. The need for spatial reuse to manage co-channel interference from multiple BSSs. Then the need for multi-user modes, whether it's downlink multi-user MIMO or trigger based on the uplink OFDMA. And then moving on to multi-link operation, and then future looking at Wi-Fi 8 at coordinated spatial reuse or multi-AP coordination. All of these are really significant MAC layer enhancements. Okay, next slide, huh? So the point is this, that as the scenarios and the KPIs for these scenarios now scale, they scale in dimension, in actual physical network size, as well as the inherent stack complexity. As we have just listed, these are all significant new MAC features. Correspondingly, there are some PHY enhancements to keep track of. So the sort of the product of looking at network scale KPIs, along with the inherent complexity of these MAC and PHY layers, is really where the issue is at. Okay, next slide. Okay. So, these are scenarios on these slides that are taken from TGAX as sort of a network simulation scenario document, where it highlights some of these aspects. One is the analytical or performance simulation, whatever be your tool, the complexity of doing some real analysis, right? Second, there's an increasing variability in the types of traffic. Increasingly, from just throughput as the KPI, we have heterogeneous traffic, several of which, particularly the new ones like video conferencing, like now, or gaming, etc. XR traffic in the network, all demand latency be perhaps more significant than just mere throughput, right? So heterogeneity of traffic, okay, the need to manage at scale network, multiple BSSs in an increasingly complex network, cross-layer network stack. This is what leads us to the next slide, the summary of kind of the challenges, right? That you have new features, but in order to understand how these new features work in the real world, this is a fairly daunting task. And the reason we know this is a daunting task, Sri has already laid out some of it, is that these features went into the standards at various points, Wi-Fi 6, 7, and we are looking at 8. And then after some initial enthusiasm, whereupon the engineers from all the world's best R&D units and vendors came together, put these ideas into the network. When those features actually get into a product and it gets deployed, here's what you see. So what we have shown here is kind of screenshots which show that features like OFDMA, all right, okay, or multi-user MIMO, they are by default disabled. So for us as kind of academic researchers, this is a bit of a head scratcher. Why? Because if these features were really sort of moving the boundaries along towards supporting these new use cases, and there was consensus that they should go into the standards and then show up in the products. Why do you turn it off? Okay, and the reason you turn this off is that this is a really complex problem operationally to manage. Okay, and frankly, as I said, somebody is having done standards. The idea or the initial sort of hypothesis which went into adding these scenarios, they were justified based on limited work, because everybody has, limited time resources. You're always, chasing the next standards meeting. For those of you who do that, every 2 months there's a next meeting. And so there really hasn't been the kind of in-depth study, that is necessary to figure out the big question. Next slide. And really, I will exemplify the big question by using 2 examples that already has been mentioned. One is downlink multi-user MIMO. So that this has been set up. It started off, well, it was already in 11 AC, didn't show up in products, but it is mainstream now in Wi-Fi 7 and with AX. And so with transmit beamforming, okay, from the AP to multiple clients, it seems like a fairly obvious, bet that one could increase throughput by sending multiple streams simultaneously to multiple users on the downlink. All right, and to do that, of course, one has to, sort of pay the price, which is you have to do channel sounding and get channel state information, right, as shown in this slide. Okay, such that the source, in this case the AP, can do transmit beamforming on the downlink subsequently during the data transmission phase. Next slide now. Okay, so it seems like a fairly reasonable idea, and soon after this was implemented, and actually a few of the AP vendors, right, I showed you the screenshot of the config file of a TP-Link AP, right? People put it to test. And, one of the more well-known results quoted actually from an industry, I think from a testing house, quoting one of the early downlink multi-user MIMO-enabled APs, was this completely counterintuitive or surprising result, which is shown here. So if you look at this, the inset, this is an ASUS AP for which this test was done. And so if you look at the panel below, there are 2 colors. The magenta dark color represents, as per standard notation, an AP with 4 antennas. So 4 cross 1, colon 1 is AP with 4 antennas, 1 user, 1 client with a single antenna, right? So that's a sort of a single user transmission. And then the light blue is same AP. Now you have 2 clients, okay, each with 1 stream, right? Each with 1 antenna and 1 stream. And so this is single user MIMO, and it performs better, right? Okay, when you are able able to send relative to a single user. Sorry, in this case, the multi-user MIMO, okay, 1 stream per user, does better than single user MIMO. However, if you look at the top panel, if instead of clients having 1 antenna, each have 2 antennas, right? Then the single user MIMO does better than the multi-user MIMO. All right. So this points out to the following fact, right? So you have high channel sounding overhead, first off, right? Okay. Issues of, spatial correlation between clients as a function of both their physical geometry, their spacing, as well as what the channel induces in terms of correlation or interference between streams. So, the reason in the top panel that actually multi-user MIMO counterintuitively does worse than single-user MIMO is that you have these 2 streams, each to 2 users, and there's inter-user interference between those 2 streams that was not mitigated, right? And finally, when you have mobile devices, so this was just, a scenario when you just have these users static, but when they move, okay, you have further issues of, how fast do you have to do the channel sounding, so-called the staleness problem. You have to update the CSI, right? All of which makes this issue complicated. Next slide. Now, same with one of the other things that she mentioned, spatial reuse. Just like you mentioned, we heard a lot about spatial reuse from major vendors about a few years ago, and then the enthusiasm sort of dropped off, went off a cliff. And again, let me explain this. spatial reuse was encoded in this new feature called BSS color, right? Okay, which was introduced a new knob called the OBSSPD. This was another threshold for measuring the RSSI from a overlapping transmission in a neighboring cell, right? Okay. The whole idea is that having this feature, a field for BSS color stuck in the MAC header would enable simultaneous transmissions wisely. The whole idea of enabling simultaneous transmission is that you are able to get multiple simultaneous packets being successfully transmitted and received. Next slide now. Well, in the standard, okay, this sort of wise use of OBSSPD is encoded in this so-called, the transmit power back of mass, which is shown at the bottom left. Now, as far as I can tell, there has been no serious investigation as to the justification for this transmit mask. Is this mask in any sense optimal? Okay. And again, this leads to a lot of questions that spatial reuse, just like downlink multi-user MIMO, can be a double-edged sword. In some scenarios, it may pay off, and in other scenarios, it will actually have the countervailing effect. It may actually lead to worse throughput, right? Next slide now. All right. So anyway, all of these point to the fact that as these new features come on board, the overall network management and optimization problem gets inherently more complex than was originally intended, and the simpler use cases that were used to justify inserting these features in real life, the real life throws curveballs, and you get unanticipated results, particularly when some of these features start interacting with each other. Next slide. Okay. And so Wi-Fi, looking ahead to Wi-Fi 7 and then 8, all right, one of the key new features is multi-link operation. So again, multi-link operation, again, sounds very logical. You have basically carrier aggregation. You can use one band in 2.4 and another in 5. In the North American context, you can have tri-band devices, 2.4, 5, and 6. And the whole point is this, that by aggregating bands channels across different bands, you get larger throughput. Obviously, the more interesting question is that can this be used not just for throughput, increasing throughput, but to lower latency, right? But in order to lower latency, one needs to look at at the protocol stack, whether the scheduler, in this case the traffic controller as shown in that green box, what knobs does it allow? What algorithms can be enabled in that controller in order to lower latency? I won't say too much more about it because How will talk in greater detail with examples from MLO. So next slide now. Okay. So as these new features come on board, I repeat the point, how they are going to be actually used in practice, there are lots of both issues and challenges, and which translate to opportunities. Finally, next slide. Okay. Oh, I will skip this. This is looking at Wi-Fi 8, the next standard, and one of the key features in this next standard is about, coordinated spatial reuse, CSR, or multi-AP coordination, which I will skip over. And I'll kind of end, next slide now, by basically pointing out that, a lot of us are sort of at the transition of what you call cloud Wi-Fi. So essentially, as network management gets more complex, the need for network operation and the insertion of AI/ML type tools will be inevitable, right? As you've seen, complexity, whether inherent in terms of dimensionality or whether due to the complexity of the cross-layer stack and the interactions that we have pointed out, whichever be the motivations, the current architecture, particularly of the so-called RF controller, which manages a suite or a set of APs, that is going to change. In terms of cloud Wi-Fi, that architecture is going to get more softwareized, and AI/ML type approaches, will become, a part and parcel of, at least some part of it will be part of the stack, for the more real-time aspects, and the others maybe operational at longer time scales on a nearby data center. So with that, I'm going to stop and hand over to Hao. He's going to discuss the role of NS3 in network simulation.
Yeah, thanks, Dr. Roy. So this is Howie. I'm currently a postdoc fellowship at University of Washington with Dr. Roy. And yeah, thanks for the great introduction of the different challenges and opportunities with the involving of the Wi-Fi standards. But however, the major issue Dr. Roy has showed is that we need a detailed validation and the investigation of those new features to see how this going to perform before it actually being implemented and widely used in the real scenario in our daily life. But how can we achieve that? And NS3 is kind of tool that can provide this opportunity, basically provide the software model of the network protocol stack to conduct the performance evaluation studies for different protocol, different standards. And basically user can set up the network scenarios with a real world implementation, real world like scenario and different traffic type, try to study the performance of the different networks. And NS3 kind of make this easy by open source and provide the abstraction of the different network protocols. So in general, the NS3 is a packet level simulation. Basically, it will generate the packet from the application layer and go through different network protocols with some socket APIs to the transport layer and finally go to the Wi-Fi, Wi-Fi MAC layer and went to the wireless channel or some other network topology. And eventually we'll gather the latency performance, the throughput performance, user reliability KPIs and help us to better understand the network performance. So the key of this simulation tool is that it can help us to avoid some real implementation and easily scale the network size, especially for the multi-BSS scenario that we will have multiple small cell networks and we want to each other. It will be extremely expensive to build in the real world. And another benefit is open source, so everyone can contribute to it and can do the validation and share the results openly. So some main attributes of the NS3 user, it may require some experience of the Linux or Mac OS, and also some experience about C++. Then for the Wi-Fi, we need to have a better knowledge of the Wi-Fi protocol stack. Here we list the main NS3 tutorial page for the reference if you like to start to look at the NS3 simulator. And what's the beneficial and what we need for the Wi-Fi design study, by involving the standard. So in general, the objective is we try to maximize the throughput and minimize the delay for different users through a different problem rate control, link adaptation, scheduling, and also some power control, some interference aggregation problem. And then we want to collect the user experience KPI like throughput latency, depends on the end-to-end details and all the different kind of traffic like gaming, like different congest control protocol, and also some prioritization around the different queuing protocols. And also we want to test in the real world scenario, like IEEE TGAX defined scenario for some indoor scenarios like residential and the enterprise scenario and the different simulation methodology, including the channel model. So to achieve all of this, actually the packet level simulator like NS3 can help us to develop different modules and to run a large scale simulation with thousands of nodes in a very large scenario. And these are the case study we want to conduct, and NS3 can actually help us to achieve that. So a brief introduction of the NS3 Wi-Fi module. So the Wi-Fi module is into the Wi-Fi net devices, and then it's a MAC layer mainly consists of the channel access manager and some TXOP and some middle layer to control all the channel access like the DCF and the EDCA protocol. Then the packet will go through into the Wi-Fi PHY abstraction. Basically, it will take care of the sending and the receiving of the frames through the wireless channels. So it will take the power as the input and go through some traditional path loss module. Eventually, we get the receive power and the SNR to get the packet error rate through the PHY transmission. So it's a pretty abstraction based on some like other simulator like MATLAB, but it can effectively module the PHY effect. And yeah, then detail of the MAC operation. Basically, a frame is first queued into a Wi-Fi MAC queue, and then we will have the channel access manager to start the DCF countdown to get the channel access, and it will, if we choose the EDCA, we'll use the EDCA operation and then get the channel access to start the transmission. We can then configure the AMPDU, and depends on some scheduler inside it, we finally can transmit the PSDU into the PHY, and finally as a receiver we can process it to get the whether a frame can be successfully decoded as a receiver based on the PHY abstraction, and then we can update the stats at the transmitter side based on the ACK etc. to have an updated scheduler of the NS3 MAC operation. So in general, the question is how we can use the NS3 Wi-Fi modules to conduct our own research. Basically, from my experience in the past few years, from our group, a good start point would be start to validate the NS3 modules, because NS3 is an open source software development, and as we know, there are so many new features ongoing and busy developing. So how we can trust the results, especially when the scenario come really complex. So a very good habit is to start with some validation of the NS3 module with very simple scenario. So I'm gonna show with one example later, and to show how we can validate the NS3 through some theoretical module like well-known and Bianchi module for the Wi-Fi MAC layer to predict the throughput and delay. And then after that, we have a much better understanding of the new features of the NS3 implementation, as well as what we can expect from the different scenarios. We can start to build new scenario or explore the different parameters. Like we can change the power, change the MCS rate, and scale the network from the single cell to multi-cells. Finally, that's our goal. We want to actually build or test some new system level algorithms, some new features evolving from Wi-Fi 7, Wi-Fi 6 to 7 to 8, and even like some much more advanced machine learning algorithms. So in the next, okay. And another thing is a recent feature that we added into NS3 that we can track at the PPDU level about the KPIs, especially in the overlapping scenario, to see whether a PPDU is collide with each other or it's a successful transmission. That could be very useful when you scale the network size and to get much detail about what's going on in the network. Then in the next few slides, I'm gonna introduce specifically with the latest 11BE MLO feature, and to discuss how we start to validate the delay and extend to more complex scenario, finally try to optimize the network performance. So this work actually, we collaborate with Huazhong University of Science Technology in Wuhan, China. And also we have some fairness coexistence study with IIIT Delhi. Yeah. And so Let's start with a very simple scenario. That's just a single BSS, and the target is we try to analyze the delay of the from the Wi-Fi MAC layer, and the topology should be very simple. That AP in the circle, and there are multiple stations on a circle, very close to the AP with a fixed MCS on each station. So the assumption here is there's no phi errors. All the station can hear each other. So the errors mainly come from the DCF collisions. Basically, when two nodes choose the same countdown value, it will collide with each other. And the traffic module is also simple. It's just the uplink only traffic, but we use a Bolognese arrival module for the traffic with a rate of lambda. The lambda is defined as at each tau t. Tau t means whole transmission, so it includes all the headers, payloads, sieves, and ACK times. And then every tau t we will have a lambda. So for all the network, there will be n nodes. So the aggregated lambda head is defined as n times the lambda. And the major KPI we want to focus on now is the delay. So for a single BSS case, we split the delay into three parts. The queuing delay basically is measured between the packet transmit into the MAC queue, and it becomes a handoff line delay. So that's the duration of the traffic is in the MAC queue. And then when it go to the first packet in that queue, it start to back off and count down. That's a DCF back off delay. And then it goes through the wireless channel, so it will have a transmission delay. They say it's a difference time between the first transmission until the packet is dequeued from the TX buffer until it's successfully received. For all the retransmission, will automatically has a higher priority, put it directly into the head of line the queue. So we define the main access delay as a components 2 plus 3, and then the queuing delay should be depends on the how many packets are there and some other scheduler. And another components we want to talk about is as we increase lambda, the traffic traffic load would increase as well. So due to the DCF operation and the overhead of the MAC layer, we define a lambda star, which means when we increase the lambda, the throughput of the network won't increase. And we can see the lambda is less than 1 simply because of all the DCF overhead. And then as the number of node increases, which means more collision happens, so the lambda star would be also decrease in those cases. And now here, basically, I don't want to talk too much about the mathematical derivative. It's from the Markov chain module of the DCF procedure. Then we can get some expected delay for different cases when the saturated, which means like there always be a packet to transmit when there's an opportunity. So you may end up to high collision probability, and they have a very steady state Markov chain for the back-off window, these components. And for unsaturated, we actually can approximate the access delay is simply the transmission duration, the tau t, plus the back-off window size related to the access delay. So that's because like when the traffic load is very low, there will be no collision in the network, and you also don't have to wait for another transmission to finish. In general, we create this plot with these analytical formulas equations, and also the point is for the NS3 simulation. We can see the NS3, the analytical module can predict the NS3 simulation results, and they quite aligned with each other. So that's basically the first step we have done for the validation. Now we have relatively confident on the NS3 module and how it perform, and we can predict the performance with some mathematical formulas. So the next step would be how can the new feature, especially the multi-link operation, help to decrease the delay? So I think Dr. Ryan has mentioned about the MLO. Basically, it's just a link aggregation, and now we focus on the STR mode, the simultaneous transmit and receive. So the two links are actually running DCF independently. And for the validation scenario, now we just want to extend it to MLO first, which means the network only has MLO devices, and still we use the uplink traffic. And for simplicity, we only have two links like 5+6 and all the same bandwidth, all the same power. And the assumption is there's no 5 errors. Basically, it's same topology, just add additional link. So then, naturally, when you have two links, there will be a question like how you're gonna put the traffic into two links. So here we just have a very simple module that we call it random policy. So each packet at the upper MAC queue, we're gonna split into two links with probability P. So in this case, P equals 2.5, so with equal probability because two links are identical. So there's no difference in these two links, and packet should go with equal probability 0.5 to 0.5 to each link. And with that simple scenario, I think it's quite straightforward to predict throughput. So now we just simply have two links. The throughput is actually 2 times the ML links. The saturation point, the lambda star is also 2 times because now we have a double the capacity of the link. And then for the delay, we can now focus on the end-to-end delay. Basically, we plus the queuing delay and the media access delay, we can see still the saturation point would be double because now you have two links. And another component I want to mention here is when you have two links, the before like you reach the saturation point, the dominant of the delay is the access delay. At some point, like the queuing delay will increase significantly. So it will become the dominant after you reaching or very close to reach to the saturation point. So this is a but most of the time our network will run in the unsaturated cases. So we can focus on the mean delay in those cases, and because if we including the queuing delay, it will just go to infinity when we have a very high load in the network. So in the next slide, we just focus on the mean access delay. For the relatively thin lambda, we can see that the mean access delay of the MLO is better than the single link operation because now you have an additional link, which means you can access channel while the other packet is transmitting in the other channel. And also we use a simulation as well as the analytical model. We can see it's still quite close. So we can also predict the delay performance, especially the mean delay performance for the MLO cases. Now that's the second part.
Sorry, how can we just maybe have a couple of minutes more?
Yeah, sure. That's really really close to that. Yeah, so that's the second part. We just changed the parameter to the multi-link operation. That's a simple extension. And now we come to the real question and real scenario. In the real world, we know that 6 gigahertz may have a lower power, but less congested because it's a brand new channel. And the 5 gig, we may have more traffic, more stations, but relatively high power, so we may end up use a high MCS. So now the two links are not symmetry. How can we design a traffic splitting algorithm, like to minimize the delay, especially for the For example, the XR use cases, which you have a bunch of traffic to transmit. So here, besides the random policy, we have some other policy. The first one is the second one is a proportional link PLR policy. Basically, it's based on the transmission, the MCS. So it try to mean the transmission delay based on the phi rate that each link can achieve. The second one is greedy policy, that it try to access the channel when the first backoff window of the each link comes to 0. So it actually means the DCF backoff delay. So these 3 policies actually can have a different performance. So the random policy didn't take any consideration of the asymmetry of the 2 links, so it has a worse performance, right? But as we increase the VR traffic rate with a different MCS on each link, we can see in the case 1, the high MCS case, the greedy policy has the best performance. While in the second case, lower MCS rate case, the PLR policy has the best performance. So basically, it means as the environment change, like not all of the policy currently we design has the best performance over the different cases. So that's raise the question, how can we optimize and try to propose some new algorithm for the traffic splitting? And even more, the environment can be very complex. You may not know the traffic type of other topology, and there may be some other interference, and the power level and MCS could be very different. Then how can we start to optimize the MLO performance to get the minimized delay? Would be like in the future what we want to study. So basically, that's lead to the third part. We actually want to study a new algorithm with a different setup, different cases. And as I mentioned, we have an analytical module to validate the simulation implementation. And through that module, we can try to have some optimal solution, some algorithm to get the optimal solution. But it still depends on some assumptions. If we remove those assumptions and directly interact with the environment, we actually has an NS3 AI module that can provide the RL-based algorithm using this module to learn and adapt from the environment to get a much better learning process and through those hidden properties and try to optimize the network performance of the multi-link operation. So this would be some future work we are doing now, and also that shows how we can use the NS3 to study and propose a new algorithm to actually benefit the Wi-Fi community. Yeah, I think that's all for the presentation.
Yeah, thanks, Sumit and Hao. I think we'll take some questions. While anybody has a question, please put up your hand. Mic runners will come to you. I have a quick question for both of you. Sumit, has there been any work done where you have actually used real-life equipment in whatever scenarios which you think might be suitable, and then compared it with some of your NS3 results, and have you found any disparities, or have you found close to simulation results? I mean, what has been your experience? Maybe just a thought on that.
Okay, Shay. So, one of the real reasons to use a simulator, as you know, that when you're looking at, sort of fresh hardware, which is, not available widely, certainly, their drivers have not been reverse engineered, right, or open sourced, okay? But the kind of things that you're talking about is really hard to do, right? Mm-hmm. So network simulation has a very strong case when you're looking at, it's essentially the scenario that you want to look at new features, the hardware is not readily available, right? And so the short answer to your question is, much of our work is done in collaboration with the Wi-Fi vendors. The Wi-Fi vendors, they run their, own test setup. They don't expose it to us, right? Okay, so any kind of quote unquote hardware or testbed validation versus NS3 validation is really up to the vendors. Because NS3 is open source, and as I told you, anecdotally we know that every vendor has a team using NS3 inside there. Okay, for academics on the outside, you're at, as you can guess, at the mercy of what vendors who are typically closed will or will not repeat.
Okay, thank you. So I think let me relay the question, Shir. Yeah.
Yeah, thanks, Sumit and How. This was a wonderful session. Just one question in terms of the Wi-Fi 8, because things are still under the works, and so if we want to use this NSC simulator, what's the capability or the packages available as part of anything that we want to try on the Wi-Fi 8, which is still under the works?
Did you hear it, or do you want me to relay it, Sumit?
Could you repeat the question, please?
So question is upcoming Wi-Fi 8. If somebody wants to use NS3 to maybe evaluate some of the ideas coming up, etc., is there already something that they can start with, etc.? Any comments?
Okay, so let me ask you: is the question asked from an academic perspective, academic researcher, or from an industry vendor perspective?
This one was an industry vendor.
So as I said, I don't know what vendor the questionnaire represents, but all the major vendors we know for a fact have NS3 teams, right? And here's the issue, right? Most of you know with open source, right? The open source has this dilemma. Is the free riders problem, right? Everybody expects that things are given to them, right? This is the sort of the bias in that question that you have an open source tool which is ready to go. That's never the case, correct? All right. So open, when you come to open source, you'll have an imperfect tool. So the short answer is there'll be some features of Wi-Fi 8 that the existing open source dev community has implemented. There'll be many things that haven't implemented, which is exactly the reason that commercial vendors take a branch, fork off what the open source community provides, and then do their own internal development. Okay.
We have one more question. Maybe you'll take that. I'll relay it to you. Yeah.
Thanks, Dr. Sumit and How. Could you please go to the slide showing the use cases and their typical throughput?
Which one, so that I can relay that? Can you be more specific?
The slide showing, let's say, VR, AR, and their typical throughput was like 10 Gbps. And
How, I think it was your part where VR, AR traffic and throughput. If you could go to that slide,
no,
please.
it was one of the initial slides from Dr. Sumit, I believe.
It was Sumit's slides, maybe even earlier, where there was some VR, AR throughput results apparently.
The typical use cases, applications and their throughput.
Is this the one, Vinod?
No. It was in Dr. Sumit's presentation.
Yeah, can you go up a little bit more? Let's see if we can, otherwise we'll do it offline.
Okay, let me still summarize the question. At least from the end, not from NS3 perspective, but from MLO perspective, if some of the use cases are link aggregation, latency reduction, and let's say fairness with respect to the older clients. But if VR, AR applications are the only ones that go into Gbps level throughput expectation, and if that is not there in a particular deployment scenario, can MLO even provide any benefit at all? Is there even a benefit?
Okay, let me summarize. Maybe let's see. So to summarize the question, Sumit and How, the questioner asks whether in some of your results you had some VR, AR traffic. So his question is, if my deployment doesn't have that VR, AR traffic, is there evaluation of some MLO that any results available? Is that the question?
No, if without VR, AR, if the typical throughput scenario per station is only in the order of few tens of Mbps,
is MLO useful, etc.?
Is MLO even useful needed?
So his question is, if there is no gigabit, etc. traffic, is MLO really useful in your experience? Any comments?
Sure. Yeah, How, you want to answer? Yes, the short answer is yes. Go ahead.
So one big question is not just for VR, AR use case. Maybe I can go to these slides. So we just talk about 5 plus 6. There would be 2.4 plus 5 plus 6. So think about the power limit of the different bands is different. So one thing, it would be useful to extend the coverage, like the 2.4 will have a better propagation, and it has a relatively higher power and better MCS at the same distance compared with 5 and 6. So in some cases, it can help to provide a better coverage in the indoor scenario. And also, if you combine those 3 bands, especially 6 gigahertz band, so now you can have another benefit is relatively clean. So you can move to a clean channel if you detect there's some much more traffic on the 5 or 2.4 bands, you can automatically change to 6. So those are some other benefits that are irrelevant to the VR XR use cases, but just to have a better channel access condition and also to extend the coverage.
Okay, I think, thank you. In the interest of time, there are still a few more questions, but maybe we'll ask them to contact by email. So thank you so much, Sumit. And now, it's late evening for you. So it's good. I hope that we'll have more NS3 enthusiasts. Mukulika's talk is also there later today. So some more NS3 will come in, one of your collaborators. So we hope that we'll see you in person sometime soon. And just to make, there'll be a tree planted in 14 Trees Farm as a token of appreciation for your participation. We'll send you the details. You can track the growth of the tree as well. Thank you once more. Big hand for them, please. Thanks a lot. Thank you, Sumit. Bye. Thanks, Hao. Bye.